All right, as for today, we're going to finish up the last little bit of regression. And we left off talking about outliers. One other big concept that we've talked about kind of tangentially, but is very, very important, is extrapolation. That sounds like a complicated word, but it really just means predicting outside the range of your data set. And when you do that, your predictions lack reliability. All right. We also talk about this usually in terms of faith. I don't have a lot of faith in that prediction. Now, we predict outside the range of the data all the time. This is what is to say predicting the future. All right. There is something that we predict every day. All right. And we know that you don't have a lot of faith in that prediction. What gets predicted every single day?
The weather.
The weather. All right. The weather gets predicted every single day. And we know that, right? Tomorrow's weather. Okay, well, gosh, I don't know the chance that they're actually correct, right? They even say, oh, 50% chance it's going to rain, which even they have like a quantified value on what's going to happen. All right. They predict the weather 100 years from now. They do it all the time. I have a lot less faith about that prediction. I have a reasonable amount of faith about tomorrow's weather prediction. And so that's what extrapolation is. It's predicting into the future. Let's look at a simple example here. The ACT scores and college GPAs for 8 students were recorded in order to determine a relationship between the two measurements of academic success. The data set is listed as StatCrunch, ACT versus GPA. So I have a bunch of ACT scores here, and I have college GPAs. So, all right, when we calculate the regression line, and I can do this in StatCrunch, stat, regression, simple linear. I'm using ACT score to predict college GPA. And I will add my additional graphs. And StatCrunch gives me the equation GPA equals negative 0.91 plus 0.14 times ACT, our standard y equals mx plus b equation. So with that, when we calculate the regression line, it yields as that we just saw. I want to predict the GPA of a student who scored a perfect on the ACT exam, and how much faith do we have in this prediction? So the general concept, predicting with StatCrunch, a perfect on the ACT exam is a 36. So that means, all right, just like y equals mx plus b, I'm given a particular x and I want to find my y value. Given an ACT value, I want to find the GPA. And this is a real strength of regression, because the simple concept is that all you have to do is replace that value ACT with the number 36 and then calculate that value. What's even better about that is that StatCrunch actually does that for us. If I go back into options edit, and right here, it says prediction of y. So I put in that value 36, and then I hit compute again, and down here at the bottom, it did that calculation. So it says with a x value of 36, the y prediction is 4.220. Now, that would be the same calculation if I did 0.14 times 36 plus negative 0.91. It's just StatCrunch does that calculation and no rounding error. So I even rounded those values. So StatCrunch makes the exact calculation. Now, here's the problem. In college, what is the maximum GPA you can get? 4.0. You cannot have a GPA over 4.0. All right, that's why they say, oh, 4.0, that's the best you can do. So the question is, okay, this is super weird. Basically, it says the calculation didn't work. Here's why. If we look at our data set, our data goes from the X value 15 up to the X value about 33. The value 36 is over here, which means, okay, it's just past the range of our data set. This is what's known as extrapolation. I'm predicting outside the range of my data. And be aware, I'm not predicting very far outside the range of my data either, but just a little bit outside the range of my data, your data shape may change. From 15 to 33, the data looks very, very linear. Well, the problem is what happens from basically 33 to 36? The data plateaus, all right? It flattens out and the shape changes. And that's the problem with extrapolation. When you predict outside the range of your data, the prediction is not as reliable. And so when we predict this value, we always then talk about, all right, how much faith do we have in this prediction? Well, in this prediction, I have no faith in this prediction since the maximum GPA in college is 4.0. However, that's not the only reason, all right? This one is very obviously false, all right? But a lot of times we might not know we have a maximum of what we're talking about or a minimum, all right? And so it's always really about, we were extrapolating here. All right, we have to be careful of extrapolation, that is predicting outside the range of our data, because those values, all right, lack reliability. And that's basically what this says, all right? We need to basically predict with caution, all right? Because, all right, can you predict tomorrow's weather? Yeah. Can you predict after that? Yeah. Can you predict a month from now? Okay, now I'm starting to get worried. All right. There is no hard and fast rule here. It's just basically you need to say, okay, if I'm outside the range of my data, I was like, I don't know. I was like, I got to be careful here. I can't fully rely on that prediction. All right. It's just like things like the stock market, derivatives. All right. All those things, you have to be careful with the prediction. What happens tomorrow is always dangerous. One other big thing, all right, and we already mentioned this a little bit, but I want to emphasize this further. Lurking variables are often the real cause. Everything we're looking at in regression and things about your project, all of that is observational study. There is an association between this and this, right? There is a correlation between this and this. It's not one thing causes the other, all right? We talked about that the birth example and the storks, right? Storks don't deliver the babies. There is a strong correlation between the number of storks and the number of births, all right? But do not say that this causes this. Simply say, these two variables are correlated. That's all we are able to show with regression. We cannot prove one thing causes another. In order to do that, we would actually need an experiment. These are almost everything we look at, all right, is an observational study. In order to prove cause and effect, we would have to actually have an experiment. And it's absolutely fine to say two things are associated, all right? Just be careful of the strength of your conclusion. All right, so let's look at a couple examples. So the Consumer Price Index, CPI, tracks the prices of consumer goods in the United States as shown in the data set CPI versus year StatCrunch. Basically, it indicates that an average item costing $18 in the 1920s cost $240 in 2015. All right, basically, that's how inflation works. So first of all, what do we see in the scatter plot? I want to describe the scatter plot. When we describe, we identify three things: direction, form, unusual features. Okay, so the direction. Is this positive, negative, or horizontal?
Positive.
Positive, absolutely. Here's the tough one. What is the form here? All right, is this linear? Let's start there. No, this is not linear. And technically, that's all you really need to know. This is not a line, all right? This, all right, it's flat, 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 goes up. This is the definition of exponential. Now, it's important, not important. It's nice to be able to recognize it's an exponential, but it's most important to know this is not linear, okay? This is not a line. It's close, but not quite. And then any unusual features? Nope, no significant outliers. So the next question says, can we run a regression analysis on the data and predict the price increases over the next decade? Since this is not linear, all right, remember that we have our conditions of correlation. We have three conditions there: quantitative variables, straight enough, no outliers. So no outliers, we said no unusual features, that one's good. Quantitative variables, yes, both year and CPI, all right, are quantitative variables, that's fine. The issue comes in the straight enough condition. We just defined this as not linear, aka exponential. That means the form defined as linear, not linear, sorry, form defined as not linear, this condition fails. All right, the conditions fail, R is not useful, all right, if we were going to calculate it. And hence, we cannot run a regression analysis, and that's where we stop, all right? So knowing when to stop is important. That's why we check those conditions, all right? We check those conditions to know, can we keep going, all right? We want our conditions to fail because we get to stop, all right? There's a ton of work to be done after this, but we don't have to do it, right? Because we cannot do it. All right, let's look at another example. Marine biologists warn that the growing number of powerboats registered in Florida threatens the existence of manatees. Biologists want to investigate if the increase in powerboats results in an increase in manatee deaths. In a recent edition of the New York Times, it was reported regarding the number of manatee deaths and the number of powerboat registrations recorded in thousands for a 20-year period. Manatees is the data set in StatCrunch. And so, all right, start where we always start. Make a scatter plot of these data and describe the association. And then now we're actually finally at the point, if there are any outliers, identify these as leverage or influence points. So in unusual features, the most important thing is to actually identify the two types of outliers. Okay, so we have manatee deaths and powerboat registrations. And there's actually three quantitative variables here. Actually, we're also given year manatee deaths, powerboat registrations. The question explicitly said, all right, was there a relationship right? Marine biologists warn the growing number of powerboats and the existence of manatees. So the question actually is only talking about powerboat registrations and manatees. Even though we have year, all right, it's not helpful in our regression. So knowing what not to use, that is important. And so in this case, right, since they're warning about the manatee existence, this is a marine biologist, that's the one we want to predict. Because a lot of this is about measurement, right? Which one do we measure first? Well, you know, it's easy to measure. What is easy to measure is registrations, paperwork, because everyone registers their powerboats. We can collect that data and then predict, all right, the number of manatee deaths. That I was like, it's not easy to measure initially. All right, so stat, regression, simple linear. Our X variable is going to be powerboats. Our Y variable is then manatee deaths. And then we grab our plots, all right, fitted line, hist, QQ, residual versus X value. So we're starting with our scatter plot. You okay? Did you get it pulled up or you know? Okay. So our fitted line plot. We start with our standard stuff. What's the direction?
Positive.
Form? Mostly.
Yeah.
Mostly linear, right? Mostly linear. And then any unusual features? Yeah, okay. So that finally, all right, that guy actually does look like an unusual feature. Why are you not letting me interact? Oh, there we go. All right, so I want to highlight that point. All right, so that one I'm going to identify. Now, here's the good news, okay? So it looks like, I mean, that falls a little bit off the line, but is the line dramatically changed by that, do you think? No, it still looks like it's mostly following the data. Since it's mostly following the data, that means I think this is a leverage point, not an influence point. Now, I could verify that further by deleting it from our data, but also you can see it by, if it is kind of close to the line, that means that that's a leverage point, not an influence point. If I have a bunch of data down here and the line is being pulled up by that value, then that's what makes it an influence point. Okay, so let's see, what was that value? All right, 860.81. All right, so description, direction. we said positive. Form was linear. And so I have a leverage point at 860, 81. All right. That is literally just the XY coordinate of that point. Now I could further think about that point as well. I mean, just as a note. So that leverage point was really high out there, all right, and it was kind of on the up end, right? So I can kind of think, I was like, okay, all right, basically the number of powerboats registrations jumped up in 2021. Do we remember what was happening around then?
COVID.
That was the aftermath of COVID. And specifically, I believe in 2021, is that when everyone got their stimulus checks? Yeah. So, gosh, everyone gets a bunch of money, and then what do? They go and spend it on a powerboat. All right. So that's probably what happened around that time frame. All right. Everyone went and they got a bunch of money and they bought a bunch of powerboats. All right. Still following the same pattern, but the data jumped up a bunch. All right. Just more people had the money. So, COVID, stimulus checks. And again, those are just thoughts. That might still not be the truth. Those are just things that kind of jump out to me that I'm like, oh, okay, I think that's why the data jumped up. And that's not, that piece isn't required. It's just, we were talking. Always good. You think about why something is weird. Thinking about why something is weird helps you understand your data. All right, I want to find the correlation between boat registrations and manatee deaths. Is this useful? So that is our conditions of correlation. All right, so quantitative variables. Both number of manatee deaths and number of registered powerboats, I can take an average of those and they make sense. All right, so that one seems okay. The straight enough condition, that one I literally just look back to how we defined the form. We defined the form as linear. So that one is met. All right, the no outlier condition. The no outlier condition, all right, and I specified this before, I don't want to reemphasize this. It's actually no any outliers, it's specifically no influence point. All right, there is a leverage point. in our data. But there are no influence outliers in our data. So that condition is met. You can have leverage points in your data. It's influence points that fails this condition. All right, so the conditions are met. We may assume, no, R equals, I'll look at it in a minute, is useful. And R in this case, oh, I lost all my data. And then R 0.9243, 9243. So conditions are met, R equals 0.9243 is useful, right? And that's always what it is. And basically, by identifying R as useful, that means we can proceed to regression. So our conditions did not fail this time, so we can keep going.
So it doesn't matter like what's the R value that you have?
What this number is?
Yeah, like if the conditions are met, it doesn't matter what's the value of it?
Nope. I was like, that value is just a strength of how closely X and Y are related.
Oh,
I was like, we interpret R squared, we're gonna interpret that later. But I mean, what that number is, obviously, the whole idea is that's -1 to 1. So the closer it is to 1, the stronger those two are related. Right? But it doesn't have anything to do with like the interpretation or like the conditions like that. Yeah. Okay. Run the overall test on your model and the coefficient test for the slope. Are these redundant? So the best part about regression is the hypotheses are always the same. And I mean, I'll tell you right now, these are redundant. That's what we talked about last time. They're the exact same hypotheses, the exact same p-value, and the conclusions are going to be the exact same. The difference between the overall test and the coefficient test is only the test statistic. And this is one thing I want you to be able to identify. Which one are you using? All right, well, everything else will be the same. So even if you use the wrong test statistic, all right, your conclusions will all still be the same. The overall test uses the F statistic. And there's only one F in all of this, right? So 99.67 to p-value of 0. The coefficient test uses the T statistic. Now notice that this question said coefficient test for the slope. The only one we run is the one for the slope. So you should only ever be looking at this bottom line, right? We don't even bother with this test statistic. All right, so the t-stat here is 9.98 with a p-value of 0. That is the only difference, all right? The p-values are the same, which means our conclusions are going to be the same for both of them. So we're just going to write the conclusions once, all right? And we'll make note right now. These tests are redundant. The only difference is the F value, F stat versus the T stat. All right, but we still need the conclusions because if you only run one of them, all right, you still want to understand what the conclusions are. And in this case, all right, with both cases, all right, reject or fail to reject HO. Reject, all right. Reject HO at a 5% significance level. There is strong evidence to show that there is a relationship between, and then, all right, it's just about X and Y in context, between the number of manatee deaths and the number of registered powerboats. The number of manatee deaths and the number of registered powerboats, there is a relationship between them. That's what this test shows. All right. After you identify that, then we can start interpreting things. Because if there is no relationship, then there's basically nothing to interpret. All right. Interpret R squared, interpret the y-intercept, meaningful, interpret the slope. All right, so the R squared interpretation, this is the one about variation. Right, approximately, okay, so we need our numbers. Now here's the good news. All right, so we just pulled R. Oh, look, right here, R squared. All right, 85.43, 85.43. So approximately 85.43% of the variation in the number of registered powerboats can explain the variation in the number of manatee deaths using simple linear regression. All right, so X and Y, the relationship between them. All right, that is, and this one, the important word here, or words, variation. This is an explanation of spread. All right, the intercept interpretation. So at X equals 0. So in context, when there are no powerboats registered, so when there are no powerboats registered at X equals 0, the estimated expected number of manatee deaths is, and then we pull the intercept coefficient, that number. All right. When you interpret the slope, we're going to pull that number. Okay, so negative 45.89. Eight, nine, and then include our units. Our units just happen to be our descriptor here. So manatee deaths, and I'm going to be repetitive. Manatee deaths. Okay, this question also said, is this meaningful? Does this make sense? So when there are no powerboats registered, the estimated expected number of manatee deaths is negative 45 manatees. Does that make sense? No. All right. So be aware, and there's actually two ways to do this. All right. So actually, I'm going to call this meaningfulness 1. Cannot have negative deaths so this interpretation is not meaningful. Now, be aware, that is a perfectly legit way to say that, and that is 100% correct. Now, I'm kind of a glass half full person, and personally, I love the manatee. All right, I think they're an awesome sea creature. They're vegetarians. All right, do you know what their nickname is? The sea cow. All right, they are called the sea cow. They literally go around and they eat seaweed, like, you know, just like a cow. All right, I got to swim with them when I was down in Cancun. I was like, I love the manatee. So I'm going to think about this a little bit and be like, okay, does this make sense? I say, okay, the opposite of death, what would that be? Life, all right? AKA, death is the end of life. So how about births? And then I say, okay, if there are no powerboats registered, maybe the manatee population is increasing. It's growing, all right? And so I say, okay, this does make sense if I think of negative death as births or life, And so basically, I say, okay, this does make sense if I think about it that way. And it doesn't matter how you think about it, as long as you explain it. All right. Basically, you cannot have negative deaths. That's perfectly reasonable too. Or, all right. And now be aware the second option always takes a bit more thinking to it. All right. If we assume negative deaths is life slash births, then this interpretation is meaningful. Since the manatee population So, all right, this is meaningful since the manatee population would be increasing when there are no registered powerboats. Either of these options are perfectly acceptable, and a lot of people just do the first one, and that's what I do want you to recognize. Negative is a problem. All right, negative deaths is a problem. Now, if you can logic that out into something good, great. And you definitely should try when it's manatees. All right, I don't care about anything else. All right, but manatees for sure. All right, and lastly, slope interpretation. A, B, C, D, E, F. All right, the slope interpretation, remember this is all about rise over the run. All right, when I run 1 unit on X, all right, so basically, and X is our powerboats. Now here's the tricky one part of this one. As I increase by 1 powerboat register, but, it is here. Recorded in thousands. So it's not 1 doesn't represent 1 powerboat registration. 1 represents 1,000. And that's the tricky part. Notice it says 1,000 there, but if we go into our data, all right, all the values, 500 to 800, that's thousands. So 500,000 powerboats, 860,000 powerboats. So it's important to make sure that you're paying attention to what's in StatCrunch and what is in the problem. Okay. All right. And for that value, what's my data again? And for that value, we go to the slope number, 0.1318. 1318. Are you with me getting the values?
No.
No, I mean, do you see where I'm pulling? Yeah, that's what I mean. Okay. So for every additional 1,000 powerboats registered, the estimated expected number of manatee deaths increases by 0.1318 manatee deaths. And so if you divide 1 over 0.1318, you can get, basically it would be this ratio. 7,000 registered powerboats correlates to 1 manatee death. Now, that doesn't seem like a lot, right? Okay. I mean, that doesn't seem too bad. Here's the problem. How many people are out there? There's about 7 billion. How many manatees are out there? Is there 7 billion? No. So I've had people argue before with me, oh, well, that's 7,000 powerboats. That's only 1 manatee death. Yeah, but that's important. I was like, it's the ratio of, and also I kind of disagree because a powerboat is a toy. All right. Hey, manatee is important. I was like, don't get lost in, oh, well, the numbers don't seem that bad. Yeah, but there's a lot more powerboats than there are manatees out there. But that is the interpretation. And then one other big note, keywords, all right? And I didn't point that out on the last one, although we did have it there. All right, estimated expected, all right? This is an average, all right? So slope and intercept interpretations, all right, are averages, and we have it here, estimate expected, all right? Slope and intercept interpretations are averages. R squared interpretation is about variation. So those are key words we need to make sure we have in our interpretation. Okay, let's see. Does your analysis show that powerboats are killing manatees? No, it does not. It is tempting to say that. And I just kind of got on my soapbox and argued it a little bit. Okay. Number of registered powerboats, the powerboats aren't killing the manatees. It's probably a byproduct. And that byproduct, right, that lurking variable, that cause is humans. All right. Now, it might not be the powerboats in general, right? Everyone gets out there and they throw trash in the water. The oil pollutes the water. All right. There are underlying factors, okay, that is actually causing the manatee deaths. Okay, it's not the powerboats killing them. Powerboat is a byproduct of humans, really. Okay, and so it's very, very tempting not to say that. It's OG. No. Powerboats are not killing manatees. All right, so, powerboats are not killing manatees. All we can say is there is a strong correlation between manatee deaths and the number of registered powerboats. That's the strength of the conclusion that we can make. And the biggest thing that I always want to emphasize, correlation does not imply causation. We just talked about it, right? The cause, right? And in whatever capacity, the cause is humans. And actually, that's the cause of both variables. Humans cause powerboats, humans cause manatee deaths. Those are the two causes, right? A underlying factor is actually causing both of those things, all right? And so it's super important, no matter the strength of the correlation, all right? And this was high, right? This was a 0.92. That's almost a 1, right? It is a very strong correlation, but you can't say one thing causes the other, okay? And it's real tempting. Make sure you don't make that conclusion.
So the correlation down here is the same as the R.
Yes, that's the R value.
Oh, okay.
That's that R value. That's the coefficient of correlation, all right? That is what corresponds to that R value. R equals 0.92. Was it 92?
92.
Yeah, 92 something. It's fine.
Mhm.
And yes, that's that conclusion. Okay. H. Predict the number of manatee deaths for 600,000 powerboat registrations. What about 1 million powerboat registrations? How much faith do you have in these predictions? Okay, so we want to look at two different predictions: 600,000 powerboats registered, all right, and 1 million powerboats registered. All right, each is going to have their own prediction, and both are going to be X values in our equation. Y equals, I forgot the numbers. Negative 4589. All right, so this is our equation, all right, for registered powerboats, right? This is the exact same equation you gave us in StatCrunch. I just replaced X and Y because we like Y equals MX plus B. Now, this is the important part. StatCrunch is going to do this calculation for us, but we have to make sure we use the right values. Remember, it's recorded in thousands. So that means I actually use X equals 600. X equals 1,000. In order to make sure you transfer from context to StatCrunch back to context. That's our big job, all right? And then it's just a matter of putting that X in, but again, StatCrunch runs through these calculations for us in a flash. Options edit, prediction of Y. So I put in the value 600, and it can even do multiple values at a time. So 600, and then you just separate it by a comma. And then I can hit compute. And it gives me the two predictions. So I don't even have to calculate those. Okay, 33.16, 86, 33.16. And 85.87, 85.87. Okay, so just a matter of plugging those values in. Now, here's the other good news, all right? Manatee deaths didn't have to be adjusted, so it's not like I have to multiply that by 1,000 again. I technically divided those numbers by 1,000, put it in a StatCrunch, and it gets out the proper value. And then don't forget our units on these. So this is manatee deaths. Okay, so we talk about the reliability of our predictions in terms of faith. Oh, I have a little faith. I have a lot of faith. All right. You can say this is very reliable. This is not very reliable. All right. Either way, again, they're synonyms, whichever way you want to describe it. In order to do that, though, all right, we need to actually go back and look at our data. So we have two values, 600 and 1,000. And basically, we want to determine if it is inside the range of our data or outside the range of our data. X equals 600 is right here. That is dead in the middle of our data. That means I have a lot of faith in that prediction. That is a very reliable prediction because I see lots of values on both sides of it. It's following this exact pattern. Now, 1,000, that's over here. As soon as you end up outside over here, now I'm worried about that prediction. That is extrapolation, and that is what we said. That's predicting in the future. That's unknown. Already, this seems kind of weird, right? We got this number in 2021, right? And we don't have the data for 22 or 23 and 4 and stuff, right? So I don't know. Stuff might be getting really crazy now, right? Maybe actually the data started to really peak up, which would be tragic. Okay, right? We love the manatee. All right. So, all right. So I don't know what's happening. So I don't have very much faith in that million powerboat registration prediction. And that's how we make that determination, though. Once it's outside the range of our data set, then you need to think about what's happening. Okay, so this prediction, I have a lot of faith. All right, and that is called interpolation when it's within the range. Not important. In the range, lots of faith. For the other prediction, I have very little faith. And that is what's called extrapolation. All right. So predicting within the range of my data, I feel good. Predicting outside the range of my data, I'm worried. And those are really, that's the only two cases. All right, one last one. Check your assumptions. Now, be aware, regression is kind of funny because it's got conditions at the beginning and conditions at the end. All right, so both of those, all right, are conditions we check. And now typically when you do regression, you look at those graphs real quick. We didn't really do that, but this, I know this data is good. All right, so when you're doing a regression, check all that stuff first before you interpret a million things. All right, so we look at our graphs. How's our histogram look?
Unimodal symmetric.
That looks unimodal symmetric as it gets. All right, how's our QQ plot look?
Linear. And then positive.
We don't describe it like that. Just values on the line. okay? And because it's always linear positive, all right? Because it's identifying quartiles versus residuals, all right? It's just close enough numbers or not. Okay, so, and that's an OR condition. All right, so histogram. Unimodal. Symmetric. And that one's done. And so I don't even have to check the other one, but we will, and we did. And that is an OR condition. Both those conditions verify we can assume the residuals are normally distributed. All right, so those two conditions verify that our residuals are normally distributed because that's what we care about the most. All right, that always, all right, that normality condition that just keeps coming back, and it's come back over and over and over again. Our new condition, all right, is the appropriateness of the linear model. In order to verify that one, we look at the residual versus X value, in this case, residual versus powerboat plot. And this one, remember that looking from left to right, I want to see a flurry of points, no pattern. You see a pattern? No. All right, and that's what we want. We want to just see kind of a scattering, right? If you just kind of Jackson Pollard it, right? That you want to see a flurry of points. And so that's exactly what I want. So I see no pattern. So we may assume the linear model is appropriate. And those are our two assumptions in regression. Residuals are normal, linear model is appropriate, aka line fits the data. All right. All right, that is everything.